Different fluids were placed on a 30 centimeters plate at a temperature of 24 Celsius degrees. The plate was still at various angles until each fluid reached a steady, constant flow, and the behavior of the fluids was observed. The fluids tested were water as a nutrient fluid, ketchup as cytoplastic, hand sanitizer as dilatant, and toothpaste as Birmingham plastic. The toothpaste was tested on a plate by gradually increasing up to 90 degrees. Even at maximum field, the paste didn't move and remained static, indicating the water after 15 seconds with a minimal angle of 15.16 degrees, it started to flow normal. The ketchup started to flow steadily on a plate after 16.4.7 seconds at a minimum angle of 46.1 degrees, showing a constant flow behavior. In the case of the hand sanitizers, it started to flow at 31 seconds with a minimum angle of 29.5 degrees, and it gradually decreasing in height as it moved. These observations describe the visual flow behavior of each fluid on the plate under the applied filling conditions. To find the shear stress of each fluid, we first have to figure out the shear rate. This was done by taking the fill angles of the plate, converting it from degrees to radians, and dividing by the time it took for each fluid to start flowing, measuring seconds. Then, using reference tables, we got the viscosity of the toothpaste, water, ketchup, and hand sanitizer. After averaging the viscosity values for each fluid, we multiplied that by the shear rate. This gave us the shear stress. For reference, the viscosity were in millipascals per second, so in this way we could see how much force each fluid experiences as it flows. Once we had collected the 3 sets of data from our experiments, we plotted them in MATLAB and calculated slopes. While all these slopes came out positive, it is important to note that this doesn't fully represent the behavior of the fluid. Some fluids, like the toothpaste, never move, and the method doesn't account for factors like temperature or the specific property of the non-nutrient fluids. This kind of analysis works well for simple fluids like water, but for thicker or more complex fluids, other reference and methods are needed. The graphs show the trends, but interpreting requires understanding the limitation of the method for different types of fluids. I overlaid all the graphs into a single plot to compare the shear stress of the different fluids. The Birmingham plastic fluid appeared above the others, but there were some inconsistencies compared to what we saw or the teacher discussed in class. For example, the pseudoplastic or plastic fluid should have been at the bottom, but it wasn't, and some fluids like the nutrients appear in the middle, even though the behavior is weaker than the others. The dilatant fluid stayed almost the same, so this difference happened because the formula we use doesn't account for the special properties of some fluid, so it only works well for simple fluids like the water. In conclusion, experiments like this can be improved by eliminating around 5% of the parameters that don't affect the final results and by taking into account important factors such as temperature, which change the fluid's behavior. The condition in which experiments perform also matter. Since we are doing a very empirical way, it can affect the results. So I think by making the procedure more formal and adding some more restrictions, we can better understand and compare the behavior of different fluids.